Hello and welcome back from break. It is time for our last presenter of the day. Wayne Shoumaker is the SVP and Quantitative Analytics Manager at Wells Fargo Bank. He is an applied statistician with experience in financial services, healthcare, and various social services. He's been involved in basic statistical research, marketing effectiveness, business-to-business analytics, and various types of risk. His model validation experience at Wells Fargo's corporate model risk spans several modeling domains, such as financial crimes, fair lending, credit and operations risk, and CCAR. His team validates traditional and newer technology, artificial intelligence, and machine learning models. Such models are used within various channels to classify customer and employee behaviors for a variety of activities. Wayne has a Ph.D. in Quantitative Psychology from the University of California at Berkeley. Please welcome Wayne Shoumaker.
Thank you. I'm quite proud to be here, and I'm grateful that you showed up. It's a bit late in the day, so bear with me, and I'll try to keep this moving and a bit entertaining. When I talked to Michael Weiss about what kind of a presentation this is, I suggested, well, it's technical, but it's a bit less technical than some of the presentations that have already been offered because there's only a little bit of math at the end, and I hope those of you who are expecting a more mathematical treatment won't be disappointed. And because the domain of financial crime is so broad, this presentation is going to be a bit spotty. There's only so much one can cover, and there is a lot of ground to cover. So I hope that what I present isn't going to be too superficial. And please, I don't mind this being an interactive exchange. Some of the topics I present are not going to be mathematical, but if you have some input to contribute, you're more than welcome to it. So I have here basically 7 pages of non-technical information followed by some other stuff, and then it kind of gets a little bit technical as you go on. Wells Fargo has a fairly simple approach to defining what a model is, and regulatory guidance will, if you look at FRBSR 11.7, I don't know who here is in the financial services. I'm a validator in the financial services, and to financial crime people, a validator is somebody that is not the most desirable colleague, but we are obligated to protect the developer from inducing model risk. And so what we have is a definition that's by policy a process of inputs and assumptions to produce estimates with inherent uncertainty, and the outputs have to serve some business use. And this is sort of a simplistic representation of what the regulatory guidance says, which will include financial, economic, mathematical, and techniques to produce quantitative outputs. And that implies some inherent uncertainty. And so there is no real contradiction between the way we define models and the way the regulatory guidance describes it. And this is our policy. We require that every model have assumptions that are well-reasoned and tested, and they must be found consistent. So every model has to have a use. For financial crime, the field is reduced, but then it's also made quite a bit more complex with respect to its breadth. So we have different kinds of financial crime, and I've only listed 4 types. One type is a growing type and popular with the data scientists involving identity theft and cyber fraud. So we have online attempts to access accounts. We have bots that try to authenticate, and if successful, then the next type of model might be required, which is a model that manages transaction fraud. So that is much more traditional. However, they still have a lot of a relationship with the cyber fraud domain. And the interesting thing about both is that those are the burgeoning fields of machine learning. Whereas if you have money laundering or sanction screening models, which are a bit more traditional, those are also extremely important models. They have extremely high risk. There are billions of transactions that are processed to identify patterns of money laundering or identify illegal transactions from hostile countries. Those are more rule-based, whereas the transaction fraud and the cyber fraud models are a bit more engaged in machine learning concepts and applications. But the one thing that they tend to have in common is thresholding. So you have alerts, or you have decisioning, you have subject matter experts that get involved. If you have a transaction fraud decision, in other words, the model is determining that this is a potential transaction fraud, then the case will go to a subject matter expert. The subject matter expert will determine whether the transaction is fraudulent or not, and it takes a little while to do that. As with anti-money laundering models, which will identify through thresholding a potential suspicious activity. In that case, it gets even more complicated because the suspicious activity could go through various levels of analysis, where a subject matter expert analyst might disposition on one level, send it over to a heightened level of review, and then after that, then a suspicious activity report gets identified, gets filled out, and then sent to the FBI or wherever it is that is dispositioned. So there are various types of risk associated with each model. The financial services is all about risk. Every model has its model risk, and model risk will determine other kinds of risk, like regulation risk, regulatory risk, that is, or reputation risk, or legal risk. And so I have shown examples. There are many different kinds. I looked at 9. I don't remember them right now, but there are quite a few levels of risk that Wells Fargo recognizes. So if we keep it kind of simple, financial crime not only requires standard regulatory guidance of all financial models, but in addition, the Bank Secrecy Act, the USA Patriot Act come in. So if there's anything the financial models require, it is regulatory scrutiny. So not only are subject matter experts involved, but the regulators are involved, and it's just generally a highly regulated field for consumer lending, investment banking, wholesale banking, other kinds of domains. Basically, they're everywhere, but they're also extremely highly regulated. And the types of outcomes that financial crime models tend to focus on are inherent risk, that is the risk that's produced by the model, as opposed to residual risk, which is not produced by the model, and those are very different concepts. But inherent risk can be a construct where subject matter experts will define an additive sum of weighted risk factors, and what comes out is really this construct. Or it could be supervised. And so you have alerts that are supervised that become the labels, or you have SARs that become the labels, the suspicious activity reports, which go on to the FBI, some indicia of suspicious activity. Or you have suspicious patterns of transaction activities based on transaction histories. And that's another kind of anti-money laundering model. So basically what you're really after is, the identification of strange transaction activities that will alert the bank to the possibility of money laundering. And while it's not a requirement, it turns out that the types of, you could tell I'm focusing on anti-money laundering. I went back to, let me go back here just a moment. I went back to 4 types of for types of financial crime models, but now I'm focusing on anti-money laundering models just because that really is the remainder of my talk. And the rest are in principle similar to what I'm discussing. It's just that anti-money laundering models have been around for a long time, and they're really kind of fertile ground for redevelopment, I should say. But it turns out that for very high volumes of transactions, the models tend to be more rule-based, and they're largely qualitative. And Wells Fargo and the regulatory guidance will recognize qualitative models. They do have inherent uncertainty. They do produce outputs for. They do process inputs into usable outputs, and that is the simple form of a model as I defined it. So qualitative models do fall under our validation scrutiny. There are also the smaller portfolios, because we build our models based on portfolios, which tend to be more complex, and they monitor higher risk with low volumes of transactions. So maybe there might be a more complex wire transaction model than one that manages all transactions, and there might be a lot of overlap. So another thing that all those models have is a family of models that go together. And so one of the good things about a family is that they tend to mitigate the individual risk a little bit. And so I talked about supervisory guidance of these models. The basic foundation of our policy is FRB SR 11.7, which says basically that we need to ensure the conceptual soundness, the ongoing monitoring, and the model performance in such a way as to minimize the risk of these models failing. It also says that banks should ensure that the development of more judgmental and qualitative aspects of these models are also sound. So these do characterize anti-money laundering models, or the sanction screening models that I touched on, the rule-based models. SR 1810 is a newer regulatory bulletin from the OCC that recommended that banks consider, evaluate, and responsibly implement innovative approaches. So basically what this is a convergence of traditional acceptance of rule-based methods with the more, the flourishing machine learning domain, which is already common with the cyber fraud models and the transaction fraud models. So this is just reiterating what I said. There tends to be innovative tools used in the traditional financial crime domain, and moreover, because of the newer developments, there tends to be some interest in natural language processing. So whereas there were no models in the past, now verbal transactions between customers and employees might become classification domains, where you have classes of verbal transactions of interest, which might include anti-money laundering. There might be other, they might be. In fact, we do have models that cover classifications like that. Now, I'd like to limit my discussion to a type of anti-money laundering model, which is a rule-based model. It is from Actimize. It is a type of model that has that is not machine learning. It's not intended to be a statistical formulation, but rather it has lots of rules using transaction volumes, transaction variance, and other variables related to historical transactions to produce a score. And then those score, it might be by type of customer, type of product, timing, and thousands of thresholds based on these partitions will determine whether an alert is generated. And that alert, as I said before, goes to analysis, where subject matter experts will disposition it. So I, the validator, and my team would look at models like this and see, well, okay, we are applied statisticians. Can we do better? We're not rule-based. We don't have the subject matter expertise. So what do we do about this? Well, let's see if we can use the information that we have and try to build something, well, supervised is what we prefer. So we'll look at the suspicious activities, the historical suspicious activities that that model produced, or we'll try to build something parallel to it. So what we tried to do in our challenge, we validators challenge the models. We tried a random forest. We tried XGBoost. We tried the unsupervised isolation forest. And then we tried to see what would happen if we leveraged the model by adding on to it. So one of the hallmarks of this kind of a model, this anti-money laundering model, is the hugeness of the relative hugeness of the data sets, where 450 million transactions per month for several months and about 70 predictors gave us enough information to work on. But one of the other characteristics of anti-money laundering models and the domain in general is the sparseness of, the heavily imbalanced relationship between normal transaction behavior and suspicious activities. So you might have lots of alerts coming out of this model, very few suspicious activities, and that's typical. Most financial industries will tell you that there's a very low true positive rate out of these models. And now I'm beginning to talk about concepts like true positives, true negatives, false positives, and false negatives. And I'll get into that in a little bit more detail. But what we have to do in a case like our challenge is to balance the data. And we have to consider the possibility that some of those metrics, false positives, may not exist, because if the model doesn't produce an alert, then you don't know what you have. You don't know that a transaction is going to be a suspicious activity if the model never alerted it. You may be able to identify precision, which is the ability to distinguish an event from a non-event given what you have. But in terms of recall, which is a function of false negatives, that is the inability of the model to detect a true event, we don't have that information. So we have a censored data set, basically, in principle. This is what we have to work with the anti-money laundering domain. So what we did was we started with a random forest, and this is probably old hat to a lot of people. A random forest is one of the first things you learn in machine learning, but what's interesting about this is that it is not the methodology, but rather what came out of it. And that is the strongest predictor with minimal variance relative to some of the other variables was account tenure. And the direction was the longer the account, the likelier it was that a suspicious, of an expected, a potential suspicious activity. We conjectured this to be that customers who are likely to commit suspicious activities or to launder money or whatever, sit on their accounts for a while. And that was kind of an eye-opener for me. But among the variables that are common to models like that actimized rule-based thresholding model that I explained, account tenure was the strongest, which was really, really interesting. We tried XGBoost because it's sexy. It's used in Kaggle competitions. You stack models and you do really well. But the problem with the financial services in explaining or in leveraging Kaggle technology is that while you might have the best fitting model, and you might have cross-validation really, really down. You might have a model that is robust. But if you can't explain it, then we can't really do something with it. So anyway, that's neither here nor there. We just found that XGBoost didn't work as well as the basic random forest. So OK, we came up with our challenge model. And then we also thought the thresholds are determined by subject matter experts. So there are thousands of thresholds for this actimized type of model based on type of customer, type of product, and other criteria. So the question then becomes, can we do better empirically by determining thresholding empirically? And all we did was just generate a CART tree. The CART tree actually well outperformed in terms of precision. But as I said, we don't have a window into the false negatives. The recall is not there. We tried isolation forest, which is the closest thing to the unsupervised actimized model, the rule-based model. It didn't work out well because it is a thresholding method that requires subject matter expertise. So even though there's an empirical component where the isolation forest is an attempt to randomly partition individual outliers, and there must be some kind of a thresholding component to make it work. And we just couldn't make it work. We tried it, but it died a heroic death. So this was our approach to challenge the actimized model. The actimized model generated alerts and produced some intermediate scores for us to play with. Our supervised attempt allowed us to generate our own scores, and we tried two methods of this. We tried to actually, what we tried to do for 1 and 2 is we tried to use, OK, this is what this middle one is. Supervised add-on means we leveraged the score from the actimized model, and then we added onto it to see if we could do better. And we tried it with the actimized scores. We tried it with the alerts. And we actually improved. We tried to improve alerting, but I'll let you know in the next slide what actually came out of it. And then we tried an overlay model, and I'll explain that too. So here we tried the first attempt we tried was to take the alert flag, that is the output from the model, and see if we could improve performance. Well, it turns out we did improve performance, but the performance was similar to the random forest that we generated. The interesting thing is that the alerts popped up, but with great variation. That's what that black line is there. It's a measure of how much across the random tree, including the alerts, how much that alert predictor varied. And then we have the alternative where we tried to just include the model score. And the interesting thing about that is the actimized model score was actually well within the distribution of the most important drivers. Yes? How do you iterate?
How do you monitor the performance? What do you measure?
OK, performance is measured by, it'll be measured by either a Gini criterion or the node impurity. So it's going to be just like any other, like an ensemble of card trees. An ensemble of regression trees. And that's kind of old technology that came out in the late 80s, where the Gini criterion was common, objective function to try to optimize. There's also another objective function which is common, minimum entropy. Basically, what you try to do is settle on the minimum entropy, and that will determine the optimal tree. And I have a disclaimer at this point. I've been talking a lot about Actimize, but this is actually a copy of Actimize. So Actimize is not the exact model, it's an Actimize-like model. So what I'm talking about in comparison to what Wells Fargo has is an Actimize-like model. Okay, now I'm going to shift completely. So the reason why I brought this up is because these models can be explained through variable importance. You can use SHAP values. You can use the typical, the ranking of the collected known impurities from, or the criteria from the variable contributions for the random forest, and you can rank order the variables to show how important they are. But this is explainability. This is one type of explainability on the variable contribution level. There are other types of explainability as well. You can also build simplified. You could build linear models to explain. You could use LIME. You could use a bunch of other methods to try to explain what's going on. And they're all at the variable contribution level. And so I just wanted to go through this really briefly. First of all, to explain other contributions that are happening at Wells Fargo, where we have the text classification model. We try to see how well it would do if we were to use a logistic regression process and compare that with pre-trained models like Elmo or Glove. And then we checked the results and found that, of course, the Glove and Elmo pre-processing were superior to the logistic regression for recall. In this case, we actually were able to identify false negatives. So there's also an observation that variation among categories for text category model, variation was more stable with the embedded solutions than it was with logistic regression. So logistic regression has its good places, but machine learning is making inroads in text classification. Once again, you can take a model like a text classifier model, you can collect the contributions, average them across the features. Maybe you could take the 5 most important features and characterize how those contributions are, and this is another type of explainability. It's something that's being developed. We've tried this. We've say for a neural net, what we've done is we've taken the gradients, the backpropagation gradients, and then averaged them across nodes and summed them for each of the 5 most what we consider to be the 5 or 10 most important tokens or words, and that would give us a measure of relative importance for the words. But this was just kind of an early experiment. More is being done on this, and I haven't been able to hear some of the discussions today that concern natural language, but I understand there's a lot of development going on now in that field. So I'm not going to go on anymore about natural language. Okay, so here's what I'd like to talk a little bit about now, and I want to go back to the random forest concept. And one thing that we haven't talked about, we've talked about variable importance, but we haven't talked about individual contributions. So what is the risk to the individual, or what is the contribution of the variables to the individual? So if you're concerned about outliers, if you're concerned about individuals who are potentially laundering money, then you want to know at an individual level what the model is doing in terms of explainability. How can we explain what's happening to the individual for this particular model? And the difficulty with a random forest is that you can't clearly see what's going on. So what we tried to do is a method of explainability that takes advantage of boundaries. So random forest produces a collection of M trees. So each of, say, 10 variables has a specific value. Carried maybe 50 or 100 times, you have 50 or 100 different values that come in. And so what you have at this point are variables that, with individual values, that is values for an individual, that collect to produce bounds. So what you want to do is get an intersection of values across all of the iterations, all of the trees, so that you get one bound. The intersection of all the values for the M trees, or the 50 or the 100 trees, will give you this boundary. And what this is mathematically is really just, if you take the entire spread of all the possible values, what you have mathematically is the expected value of the entire out-of-bound region. So you can start here, like say, what you have here. What you have is a collection of what actually happened. What you want is a collection of what could happen. That is how you calculate the importance of the value of the variable given for a given individual. This is kind of similar conceptually to examining the contribution of a model with a variable taken out. But here, what you're trying to do is examine the contribution of the variable to the individual if the variable were perturbed. So that is how you examine A, the sensitivity, and B, the importance of the variable to the individual in terms of the model. So the model is the context, and the individual is being affected by the variable in what way. So what you have is a variety of values that span the boundary of possibilities, but not what actually happened. And so that works out to the bottom quantity there, which is really the probability of the value for an individual being some beta times the model probability for the case where that value equals beta. And so then the entire boundary will be the sum of that. So we took that, and we took individual values, where 54 might be, the example 0.54 might be the value that actually happened. And then you perturb that value to 0.223 to see what happens. And then you need some kind of a metric. So you could use maybe a Euclidean metric, or you could use a city block metric. We chose a metric where you just take the absolute difference, and then where the R sub ij represents the probability, the Q actually represents the predicted outcome. So it would be, in the case of an anti-money laundering model, it would be either event or no event, the alert or non-alert. So in the case like this, we calculate, if you want to take the simple value of lambda equal to 1, then you just have that calculation there, and then you do it many, many times. The difficulty with that is you don't have it normalized. So we want to take the sum across all the variable values for that individual to normalize it to see how well that variable for that individual is doing across the collection of variables. And we tried this actually for just an experiment with 10 variables for that individual. So we calculated the probability of the model, which was already there. You get it from the random forest. You calculate the probability that the value equals a certain that the variable equals a certain value for that individual, which you can get from a distribution of your choice. It could be uniform. You multiply the two together, as we did, and that will give you the predicted probability. So also graphically, what we're doing is we're taking a basis of the number of variables, and we're perturbing each one in turn a certain number of a certain percentage, you might say. So in this case, we're perturbing by 5%. This is the example for a sensitivity analysis where we're taking each variable in turn and perturbing by 5% to see how to see the impact of the model on the individual. So this is of interest to the anti-money laundering people because, as I said before, we don't have a window into false negatives. If an alert is not generated, we don't know whether the model is generating, whether the individual is conducting suspicious activity or potentially suspicious activity. And the regulatory guidance, recent regulatory attention has been on the ability of the model developers to conduct below-the-line testing. And we've been pulled along for the ride willingly to try to come up with techniques to help the developers determine the effect of a model in generating false negatives. The only way to do that is to look below the line, below the threshold, and see what the model can do where the model would not normally be operating. And we do that with this kind of sensitivity analysis. So we could also look above the line. We could conduct local sensitivity analysis on the above the line and below the line perturbations. We could look up and even further and actually conduct global sensitivity analysis or some kind of interpretability analysis on a set of values using this for an individual. So we actually tried this. And this is a case where the probability of an alert or the probability of a potential suspicious activity was 0.24. We perturbed 10 variables, 0 through 9. We perturbed 10 variables down 5% and up 5% to see what the consequence would be on the probability. And you can see the great variation there. We were able to calculate the variable importance just because of the random tree. The random forest. But because of our ability to perturb values, we were able to see how the probabilities rose and fell as a consequence of our perturbation. And that also brings us to a way to determine how sensitive the model is to a given input for that particular individual. So the next image shows a person who has probability 1. So here this person has a predicted outcome of 0. That is no potential suspicious activity. Here you have a probability 1 where almost surely you have an expected suspicious activity. And the only way you can go is down. So we perturbed down 5%, we perturbed up 5%, and those are the values we had. So that basically is my talk. I just wanted to start by talking about Wells Fargo's models in general. Talked a little bit about anti-money laundering models. I actually talked about financial crime models. narrowed down to anti-money laundering models. I talked about a specific type of model that is a rule-based and generates alerts. It's like an actimized model, but it's actually not. We challenged it with our own supervised methods. We tried an unsupervised method. It didn't work very well. I stopped at that point and I introduced something new, which we're engaging in because of new technologies. It happens to be a text classifier model, and the purpose of that model is to identify different classes of potentially aberrant behavior, one of which is anti-money laundering, and that might be inferred from the relationship between a customer and an employee in terms of the discussion, the text or other means of verbal communication. Then I stopped there because I concluded that these are methods that are all explainable in some way, and technology is, the methods are improving rapidly to be able to cover the domain with variable importances. And this is where I came to a point where individual differences might be useful. Because of the nature of anti-money laundering, you might want to be able to explain it through individual differences. So this is where I stop. And any questions? Yes?
Can you go back to the slide with the above the line, below the line?
Yeah, sure.
On your above the line test, you talked about, the observation suppressed by a rule. Sorry.
Yes.
We're talking about the above the line part with the red line, and
Yes.
I'm asking about, to go further detail of what it means. I'm just ignorant to it on using a suppressive rule on the above the line observations and what they were getting out of that.
Suppressive rule. So if you want to, that is, if you want to eliminate a rule, or you want to.
Just your statement. Your statement is.
This one here.
No, back. Yeah. It
Okay.
says, an occasional above the line observation suppressed by a rule.
Oh yeah. So.
And I'm guessing you're trying to find false negatives?
Actually, testing above the line is going to give you false positives.
Right.
Yeah. So really, what I would do is perturb a value down. I could perturb a value down. In other words, I would have already established the values above the threshold, and then I'm just conducting some kind of sensitivity analysis to see what happens above the line in terms of the ability to identify true positives or false positives.
Okay, you weren't using that to identify false negatives.
That is correct.
Okay.
The only way I could.
Okay.
That's correct. The only way I could do that is by going below the line. Yeah. Yes.
Great presentation.
Thank you.
I have a question with respect to the NLP models that you use. What type of data were you using in order to extract insights? I can
right.
understand the challenge. I was running anti-money laundering programs from Citi.
Sure.
So I can.
Well, they're unstructured text, so they could be emails or chat sessions or whatnot. But because of the heavily regulated domain, we have to be very careful about the manner in which which transactions are conducted, whether they are either online or verbally, or the complaints that are. We have to give some weight to the complaints that come to us too. So the text classifiers is a growing domain for us.
But you don't have access to the emails among the transactional entities.
Well, it's a different line of business actually. The end result is you have to classify bad behavior somehow, and this is just another domain to do it. Okay. Yeah.
Hi. Great presentation. I just
Thank you.
have two questions.
Yes.
First of all, regarding the imbalance classes, I wanted to know how did you balance the data?
Oh, we just undersample the non-events and we oversample the events. That's basically what we did.
Okay. And regarding recall and precision, so I understood you couldn't really calculate recall, but you
That's
had
right.
a benchmark data to kind of.
Well, yeah. So we actually we were unable to calculate recall for for the cases where we tried to build the machine learning analogs to the rule-based model. So we just didn't have that material handy for us to compare.
Okay. I just wanted to ask if you would prioritize basically precision or recall in such a problem, but I don't.
It's a really good question. I would put great weight on recall, actually, just because the question is, what are we leaving on the table with a model that where we don't really know what it's missing. So, in fact, the regulators have been giving us attention, basically financial services in general, attention to the ability of the model to identify potential suspicious activity without knowing what's going on below the line. We don't know how well it could be a random number generator for all we know. It could just be generating positives, biased, outcomes without really knowing how well it could do by dropping the threshold. So thresholding is a big deal in the anti-money laundering world. Yes. Yes. Hi.
Thank you very much. The question here for final performance measure. I know you mentioned some of the non-SAR and SAR. The ratio is 1 in a million. Of
Yes.
course, you didn't say about the NERS and the ratio to SAR. So can you compare before using this one, the rule-based, and also use this, how much you get the improvements?
Oh, that's right. We didn't actually, let's see, what did we do? We calculated we got comparable, you're talking about alert to SAR ratio?
Yes, right.
Yeah, we actually outdid the rule-based model substantially. I don't recall the actual values, but we did outdo them substantially.
I see. Based on your number being there's one place you were saying there's about 450 million transactions.
Oh, that's the number of transactions.
Right, in a
monthly.
month, you were
Yes.
saying if it's 1 in a million, you only generate, let's see, the
Very
SAR.
few.
Very few, right? It's
Yeah.
400, a few
Yeah,
hundreds?
it's very few. Yes, it's extremely unbalanced. Right. So we have to consider the SARs that are generated over a period of months.
Okay.
Right.
All right, thank you.
And sample from that.
Thank you. I just had a question about the false negatives. I mean, so once a transaction, SAR, has been generated, do you go back and look at other transactions from that same individual and see if there are things that should have been generated?
Actually, that's a really good question because a SAR, sometimes a SAR is time limited. Sometimes it's a part of the customer. So I can't answer that question because I don't know enough to answer it, but I know it's relevant because I've seen the differences. Sorry, it's the best I can do. Hi.
So, some banking institutions don't really consider SAR as a measure of productivity. They'd say if you have gone to an advanced level of investigation, then we would consider that particular alert to be productive enough in order to increase the volume of productive alerts, so to speak, given the data is so imbalanced. Is that something Wells Fargo has considered ever?
Actually, I don't know. There is something that is changing, and that is the domain of the restricted domain of subject matter expertise. I cannot answer that question, but I'm hoping to be able to do that soon.
All right, got another one. So, talking about your case management, going from an alert to SAR back and forth,
Yes.
did you consider any of that, and how did you consider that type of whole? Because it's a big old, long, hairy process, lots of
is.
analysts and handoffs
Yes.
into your success.
We kept it simple. No, you're absolutely right. There are various levels of how potential suspicious activity is managed, and some, I'm sure, even among models, the way that they are managed, the way that until they get to the point where they're analyzed by a subject matter expert, that management can change. But I think by the time it gets to a subject matter expert, by the time it gets to an analyst, it then goes through a long process. And a SAR might not even result in illegal activity. It might just not. It's hard to get more than just a fuzzy or basically a very basic acknowledgement that that actually means something. The best you can do is show some kind of persistent pattern that shows up and say, oh yeah, so what I'm producing here actually is robust, and that you just kind of back into the the reasonableness that way.
Are you noticing operational efficiencies? Like one of the things could be like, oh, our model seems to make it handoffs less. That there's less handoffs, or maybe there's a lot more because for whatever
Yeah, that's right. So some people will actually acknowledge that the existence of a SAR encourages more more reliance on alert generation. Maybe the threshold could be dropped or something. But that really does depend on the business. And I, the validator, am not going to tell the business what to do. It's just enough for me to figure out what's going on at this point. So yeah. Thank you. Any other questions? Anything else? You've been very patient with me, and I really appreciate your attention. Thank you so much.